Here we have problem number 10, and in problem number 10 we are asked to find the hydrostatic force that's acting upon this disc that's being put into the water vertically. And this is a square, but it's tilted. Now you might be wondering, why is it tilted? I like squares when they're upright like this, but the force that's going to be the hydrostatic force that's on this object is not equal to that that's on this object. They're going to be different. And so that's why we cannot just tilt it out to find the hydrostatic force. We need to use this one. So let me draw the rectangle that we usually draw on this object in order to find the hydrostatic force. And then what I'll do is I will split this. So what I'll do is I will draw an axis, the x-axis, but this is going to only apply for, that was not neat. This is going to only apply for the top triangle. This is not going to apply for the bottom triangle. The reason why is because when we try to find, so when we set up our y-axis, this would be x, but then so let me do that actually so I can explain it better. So my y is like this, and when I see this is going to be x, and this is going to be 2x, but this slope is what we're going to be using to set this from y to x, or from x to y. But then this slope is going to be different, so it's going to have a different y value. So we need to split this shape into two separate shapes. So this is one of them, and then the next one is this one. And so let me see what I can do. So I can try to redraw the situation here, but for the other shape. So I'll draw it over here. So this is the water. I'm trying to draw it about the same height. And then this, so right about here, I see the shape. I'll draw it in white just to get the coloring. So right about there is the shape. And we can draw our triangle here. All right. There we go. So this triangle has and what we can do here is, instead of setting the x-axis up here, we can do that, but we can instead set it down here. So this will be our x-axis, and then straight up would be our y-axis, something like this. Okay. So this is what I'm doing. First, let's deal with the integration on the top, okay? And next, let's deal with the separate integration we'll do for this kind of a shape here. So here it's going to be, remember the force, so let me write this here. Force is equal to pressure multiplied by the area. And again, we're splitting the forces into two separate things, so we need to add the two separate things. And we're doing this because the x value is going to be different for here and for here. So we can't use the same thing. We will create a separate thing. This will be x for this one. So pressure is going to be, we need two separate things. We need the distance and we need the density. The density is going to either be 9.8 times 1,000, 1.8 times 1,000, or 62.5 pounds, 62.5 pounds per feet cubed, or 9.8 times 1,000 kilograms per meter cubed. Kilograms per meter cubed. So yeah, we will do this force formula. We'll apply this for this one and this one separately because we're splitting them into two since the x values are going to be different. So we're splitting them into two separate problems, and we can separately calculate it and then add it up together. Because the main reason we're doing this, as I said again, is because the x values, we're going to have different stuff, so it's going to be two separate ones. Okay, the x values is going to be different for this one and for this one. Since the slope here is negative, the slope here is positive, it's going to be different. So this is going to be separate integration, this is going to be separate integration. So that's why we split it into two. We'll look at this integration and then this integration, add them up together to get the total force. So let's do that. So this one right here, let's see the area. The area, so let me write this as a force top. This is going to be equal to the area of this is just dy right there. Even this one is dy. And so this is just dy and then x. But we want x in the y world. And so that's why we'll see this, and we'll see 2 points here. And this actually is going to have a slope of -1. And the reason why is because we have a square. This is perfect 45 degrees. So this slope is going to be -1. So y is going to be equal to -1x plus b. B is this distance here. We don't know what this distance is. What we can do to find the distance is we know that this is a square. So let me draw this square here. And this is just tilted over. Each side is a. So a. Then the diagonal length is going to be a squared plus a squared, which is 2a squared, right? A squared plus a squared is equal to this squared, which is a squared plus a squared is 2a squared square root is equal to this, right? But then we want to divide this by 2 because we want half of it only. So this is the square root of 2a squared over 2, which is basically, so this is, let me write this over here. So y, and then this is going to be equal to square root of 2a over 2. Okay, so this is our our y-intercept. So plus square root of 2 by 2a, square root of 2a by 2. And so if we rewrite this, this is just equal to y minus square root of 2a by 2 is equal to -x. So negative y plus square root of 2a by 2 is equal to x. So that's that. We'll replace it here. So this is just going to be square root of 2 over 2a minus y. That's the area. That was the hard part. Next, we just have the density. Density of water is just 9.8 times 1,000. We're actually not given if this is going to be in meters or in feet or whatever. So we'll just assume that it's going to be in pounds or in feet. So we can use this pounds, 62.5. 62.5. Although we can use anything because it's not specified, we'll just use this one because it's just one value. It's much easier for us to work with. And that's that. And next we need to multiply by the distance from the water. So this is actually going to be all the way on the top of the water, and this is just going to be, notice that this is just going to be square root of 2a by 2. And so this, since this is just y right here, this is y. This is square root of 2a by 2 minus y. So this is just going to be integration. Remember, the distance is square root of 2 by 2a minus y. That was very small. And that's our distance from the water, from the top of the water. And then the integration we're going to be doing is from 0 up until square root of 2 by 2. 0 up until square root of 2 by 2a. This will give us our f top. Next, let's deal with our f bottom. F bottom is going to be very similar, except we're dealing with a different this thing right there. So our y value, so let me just write this out here. So this is going to be integration. We will have dy, but then this stuff is going to be different. And then this, we'll just say, is still 62.5. And then this is going to be something else as well. So those are the two things that change. Even the upper bound of integration is going to change, but the lower bound, we're still looking at 0, right? So we're still looking at this 0 here. Okay, so 0 to, so what's this top part going to be here? What's this top part going to be? Well, we need to first identify what this line is. Well, this is just going to be y is equal to x, because it's a positive 1 slope, x, this has the slope, this has a slope of m equals to 1, and then the y-intercept is just 0, so plus 0. Y is equal to x. That's beautiful, isn't it? We can just write this to be, so this is going to be just x instead of, y instead of just x. So this is going to be y. We got that, 62.5, all of this. Next thing we need to do, we got the area, we got the density, the distance. The distance is going to be a little different. So we have this up here to this down here. This is what we're trying to find. Let's first try to find, we know that the square root of 2a by 2 is this distance here. Let me do that in green. So this distance here. So this distance here is also going to be the same, which is this distance there. So that's just going to be square root of 2a by 2. So the whole distance, this all the way down, is also going to be square root of 2a by 2 times 2. So square root of 2a by 2 plus square root of 2a by 2. So square root of 2a by 2 times 2. 2's cancel. This is just the square root of 2a. But then we have this y over here as well, right? This y over there. So this is just square root of 2a minus y. That's this. So square root of 2a minus y. This is, let me erase this, make this smaller. Square root 62.5, and then square root of 2a minus y. And then we have to do the bounds of integration. That's from 0 to, guess what this would be? That would just be square root of 2a minus 2, or square root of 2a over 2, sorry. Square root of 2a over 2, because that's how up it's going. So this is the same thing actually, square root of 2a by 2. And so what the total force is going to be, so F total, the total hydrostatic force on this tilted square, this diamond, is going to be the integral from 0 to root 2 by 2a of square root of 2 by 2a minus y times 62.5. We assume that it's going to be in feet, but if it wasn't in feet, we would use, if it was in meters, we would use 9.8 times 1,000, which is actually this is the American unit, and then times square root 2 over 2a minus y dy plus the integration 0 to 0 root 2 by 2a, and then root 2a minus y times 62.5 times y dy. This is your answer. Now, you obviously need to integrate this, and you need to find the result. You will get a result in terms of a, because a is actually a number, but we don't know that number here in this problem. So you will get a result in terms of a. You can plug this into a calculator, or you can integrate it. You'll get a result. That's the hydrostatic force. Okay, so it's a long video, but this covered how to find the hydrostatic force of this interesting looking diamond. Hope you found this video helpful.